Hey, welcome back to the Modern Algebra Made Easy series. My name is Scott Hader, and today we're going to be talking about permutations. And they look like this. Basically, it's just a shift. You see that 1 goes to 3 here, 2 goes to 1, 3 goes to 4, and so on. So that's just to give you a basic idea before we define it formally. And we're going to work through an example real quick. So in this example, it gives us that sigma is this permutation, and mu is this permutation. And it asks us to compute mu of sigma. And this reads just like a composition of functions. It's not mu then sigma, it's mu of sigma. So just like in college algebra how you had f of g of x, you got to compute g of x before you can compute f of g of x, don't you? So that's what we got to do here. So first we're going to compute sigma. So if you take the first element, number 1, for sigma, 1 goes to 3, doesn't it? And then we're going to compute mu. So we come over here, and 3 goes to 4. So 1 goes to 4. And if you compute the rest of them, you're going to get this. This is basically how it works. And so the formal definition of a permutation, it's a function that's a one-to-one correspondence onto itself. You can say a shift. The range will be equal to the outputs. In other words, and also the domain equals itself, doesn't it? Because it's a one-to-one correspondence onto itself. So if we're talking about the numbers 1 through 6, the range is also 1 through 6. And since it's onto, that means that the range is equal to the outputs of the function. So we're always going to start with 1 through, if we start with 1 through 6, then we're going to end up with the bottom row being also 1 through 6. And we're never going to end up with more than one number. For instance, down here we can never end up with like 2 3s on the bottom row because it's 1 to 1. So 2 different inputs cannot have the same output. Okay. Hope that made sense. So now, this example, we got sigma and mu. Again, a little bit different, but I think they're different anyway. And it asks us to compute sigma squared of mu inverse, which you could rewrite sigma mu inverse. And so which one do we got to compute first? Hope you said this one. So mu inverse, what does that mean? It's just, if you just remember it, how an inverse function works, it's opposite. So instead of starting with an input and going to an output, we start with an output and go to an input. So if we start with 1, we're looking where we get 1 as the output for sigma. And we get it from 5, don't we? So that's mu inverse. And now we go over to compute sigma, and 5 goes to 6. And we got to compute sigma one more time, so 6 goes to 2. So, in other words, if we're looking for the result for our first number in our permutation, it reads like this. And mu inverse of 1 is 5, sigma of 5 is 6, and sigma of 6 is 2. So you can see 1 goes to 2, and so forth. And notice our result is a one-to-one correspondence. It's always kind of funny, like I don't know, like starting out I was always checking it as I was like, but it's amazing how I never get 2 numbers that are the same on the bottom, and just obviously didn't understand the definition. how it worked. Not that funny, I guess. Alright, so this time we got sigma. It gives us another permutation. And it asks us to find the order. If you remember last video, we talked about cyclic subgroups. And this is a cyclic subgroup. It's the cyclic subgroup generated by sigma, generated by this permutation. So it's an example of having subgroups and groups that aren't just numbers. They could be other things too. And this is one of those cases. They can be permutations. So this is the order of the permutation, or you could say it another way, the order of the cyclic subgroup generated by the permutation sigma. And if you remember from last video on cyclic subgroups, the order of that cyclic subgroup is you take its generator and you see how many times you need to multiply by itself to get the identity, which the identity in this case for permutations is the trivial identity, or well, trivial identity, it's kind of redundant, but it's the trivial permutation. How about that? 1 goes to 1, 2 goes to 2, and so forth. So we need to find how many times we need to multiply by itself to get the identity. And it turns out to just be the LCM of the order of each of our numbers, 1 through 6. So if we take 1, for instance, 1 goes to 2, 2 goes to 4, 4 goes to 3, and 3 goes to 1. So it went back to itself after 4 permutations. Right? And if you do it for the others, 1 through 4 are all going to wrap back around after 4 times, and 5 and 6 will wrap back around after 2 times, right? So what we're doing is taking the LCM between 2 and 4, which is 4. So the order of this permutation is 4. It's kind of cool, right? You have to admit it. Can't deny it. So one thing to note here is that sigma to some power is going to equal sigma to some power plus any multiple of 4. Since it loops back around after 4 times, you can just add 4, any multiple of 4, and it will equal what it did originally. So that's just something to remember. Okay, so now we have a question. Is this a permutation? And a permutation is a one-to-one and onto function onto itself. And we see it's onto itself, or, well, at least the domain equals the range, so we're good there. And is x plus 1 a one-to-one function? It is. Is it onto? It is. All our outputs will be negative infinity to infinity, or the reals. How about this one? Well, is x squared a one-to-one function? It's not, is it? It doesn't pass a horizontal line test. And also it's not onto, because the outputs will always be positive, but our range is all the reals. Third function, negative x cubed. Just let you think about it for a second. And that is one-to-one and onto. How about e to the x? E to the x is 1-to-1. Is it onto? Remember, e to the x doesn't go below the x-axis. Actually doesn't touch the x-axis. So it's not onto. Your outputs will always be positive, but your range is negative infinity to infinity. So here's the answers here, in case you have any question. Right, so some true or false questions. Every permutation is a one-to-one function. Well, if it's a permutation, by definition it's one-to-one and onto, so it's definitely a one-to-one function. Every function is a permutation if and only if it is a one-to-one. Well, if and only if statements work both ways. Not that you need to in this case, but being one-to-one is not enough for it to be a permutation. It has to be one-to-one and onto. So that would be false. Every subgroup of an abelian group is abelian. Always have that abelian term in these lectures, huh? Well, if we have an abelian group, then all the elements in the group commute with each other. So if we take a subgroup, a subset of that group, all those elements are going to commute with each other. So it's abelian, so it's true. Alright. And no proofs today. I don't think we had. Oh, we got one more example here. Alright. Oh, yeah. And so, find the number of elements in this set. Basically, sigma has to be in S4, which is the group of permutations with 4 elements. But one stipulation, that sigmas of 3 equals 3. So what this looks like is this. Sigma of 3 is going to be 3. So we don't know what the other ones are, but this one's fixed. So how many choices do we have for the first possibility? One could be 1, 2, or 4, right? So that's 3. Now afterwards, 2 will have 2 choices, and 4 will have 1 choice. So 3 times 2 times 1, 6 possibilities. Find the number of elements in the set. Sigma's in S5, given that sigma of 2 equals 5. Looks like this. And you can find that one for yourself. And I think we're going to end on that note today. Thank you very much for watching. Comments, questions, welcome. Criticisms, welcome. Anything is welcome. And have a good day.